Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIUA campus. Let's start with the lecture contents first. In this video, we will cover Fourier series examples and the convergence of Fourier series. Example 1. Let's look at the signal. We have a given xt is equal to sine omega naught t, and from here you can see that the fundamental frequency is omega naught. So one approach to determine the Fourier series coefficients for this signal is to apply equation 3.39. This is equation 3.39. If we want to find the Fourier series coefficients, then we can follow this approach. And for this simple case, as this is a very simple case, you can see that xt is sine omega naught t. However, it is easier to expand the sinusoidal signal as a linear combination of complex exponentials and identify the Fourier series coefficient by inspection, as we can expand this sine omega naught t, and by inspection, like by looking at this equation expansion, we can directly find the coefficients of the Fourier series. Specifically, we can express, as you know, that we can express sine omega naught t as 1 over 2j e j omega naught t minus 1 over 2j e minus j omega naught t. So comparing this right hand side of the equation and equation 3.38, this is equation 3.38. If you compare the right hand side, this side, with this equation, you can clearly notice that the a1, because there are ak, so if you put k equals to 1, so a1 ej 1 2 pi t over n, or because here we have an omega naught, so we can say that a1 ej 1 omega naught t. So we can clearly notice that this a1 here is 1 over 2j, and minus a minus 1 is minus 1 over 2j. We can clearly notice from here. So we got the two coefficients a1 and a minus 1. The other terms are 0 because there are no other, after expanding sine omega naught t, we don't have any other components. So we can generally write that ak equals to 0 for k not equal to 1 or minus 1. So this was a very much easy example. We can easily find the coefficients of sine omega naught t by inspection. So we don't need to follow the this equation, like we don't need to use the equation 3.39. This is equation 3.39. So we don't need to use that equation to find the coefficients ak. We can just do by inspection in this example. Next example, example 2. Let we have a signal given xt equals to 1 plus sine omega naught t plus 2 cos omega naught t cos 2 omega naught t plus pi by 4. We have to find the Fourier series coefficients of this equation as well, this signal as well. Now we can clearly notice from this equation as well that we have a fundamental frequency of omega naught. As with the example, we can again expand the xt directly in terms of complex exponentials. The main thing, as we already studied, that by Fourier series we expand the equation or any signal in terms of a complex exponential. So this equation can be clearly converted into the complex exponential. So 1 plus sine omega naught t, you know that sine omega naught t can be written in terms of a complex exponential as 1 over 2j e j omega naught t minus e minus j omega naught t, right? So we can expand the cos omega naught t in this way, because e j omega naught t plus e minus j omega naught t over 2, but because we have already have a 2 here, so this 2 will be cancelled out, right? So cos similarly cos 2 omega naught t plus pi by 4, so here we have an angle of 2 omega naught t plus pi by 4, so similarly 1 by 2 e j, this angle 2 omega naught t plus pi by 4 plus e minus j 2 omega naught t plus pi by 4. Now we are collecting these terms, like collecting means that we are gathering e j omega naught t together. Like here we have e j omega naught t, e j omega naught t. So we can write that one is independent. So 1 plus 1 over 2j, like this way, ej omega naught t. So 1 over 2j from here. So 1 plus ej omega 1 by 2j into aj omega naught t. And similarly, we can gather the terms together for e minus j omega naught t. So 1 over 2j from here minus 1 over 2j from here and 1 only from here. So 1 minus 1 over 2j e minus j omega naught t. And we can evaluate this equation as well, simplify this equation in this way: 1 over ej pi by 4 into ej 2 omega naught t plus 1 by 2 e minus j pi by 4 into e minus j omega naught t. Now from here we can notice that this term is a naught, as when we compare this equation with equation 3.39, as we already compared in the previous example. So this is power fundamental frequency, this is the k, here is 1 and here the term is k is equal to minus 1, and here the k equals to 2 and here the k is equal to minus 2. So the Fourier coefficients are a naught equals to 1, a1 is a1 plus 1 over 2j, or we can further write in this way 1 minus 1 over 2j. And similarly a minus 1 is this one, 1 minus 1 over 2j. We can further evaluate in this way 1 plus 1 over 2j. The j here in the denominator is now in the numerator, because we multiply and divide by j, so that j will be cancelled out and we will get the 1 plus 1 over 2j, right? And a2 here is this term 1 over 2 ej pi by 4, and if we solve this equation, we can get under root 2 by 4 1 plus j. And for the negative side, e minus a minus 2 1 by 2 e minus j pi by 4, we can get under root 2 by 4 1 minus j. And for other case, because we only have a 4 terms, for other case like k greater than 2, for plus side, and because this is absolute, it means that the negative 2 or the positive 2, we have a coefficients ak equal to 0. Now we are plotting the magnitude and the phase spectrum. Magnitude means that we are plotting the coefficients amplitudes here, right? So if we plot the coefficients amplitude here, amplitude means absolute values. We are not taking care of the sign here. So for the 0 we have a 1, right? And the other values a1, a minus 1, right? a2, a minus 2. For the rest of the coefficients, for a3, a4 is 0, a minus 3, a4, all are 0. And phase, angle, here we have to plot. So angle, how can you find angle? Tangent inverse, right, minus tangent inverse b over a. So you can just put b over a and find the angle. So for a naught it's 0, and for a1 you have some value, and for a2 you have a positive value, it has a negative value, positive value, negative value. You can calculate by using this equation, b minus b over a. What is b? For example, the j term is the b and the a term is the 1. So by multiplying under root 2 by 4, so a here is under root 2 by 4, and here b is under root 2 by 4, but in by minus sign. So you can just do the tangent inverse, you will get some value here, and you can plot the angle spectrum. So it is phase or the angle spectrum. So magnitude and the phase in terms of a polar form. Let's discuss another example, the periodic square wave. You have given this periodic square wave x of t. Now using the Fourier coefficients, you have to find the Fourier coefficients of this equation, right? This periodic square wave. So sketch in figure this one, and defined over one period in this way. So period for xt is equal to 1 for t less than this one. This is 1 for t less than t1, right? And plus minus t, the absolute means plus minus t, so t less than t1 or t less than minus t less than t1 in this way. and the 0 for other range. For example, t greater than t1, this one t greater than t1 to t2, t by 2. Similarly, from here to here, it is 0. Is a signal that we will encounter a number of times throughout this book. This signal is periodic with fundamental period of t. So this is the fundamental period from where it repeats again. So here the fundamental period is t, and the fundamental frequency you can find 2 pi over t. So the frequency is this one. So to determine the Fourier series coefficient for xt, we use equation 3.39 as we already have the equation in the previous slides. So by using that equation, because of the symmetry of the xt about t equals to 0, you can see that it is at t is equal to 0, the symmetry that follows in this way, right? It is convenient to choose the period minus t by 2 to t by 2. So like this one, minus t by 2 to t by 2, it will be a complete period. So we can analyze between this period. It will be more easier as compared to just considering from 0 to t. So we will just do to take the benefit of the symmetry, we will use this period. So interval over which the integration is performed, and although an interval of length t is equally valid and thus will lead to the same result. If you take the interval any other interval instead of minus t by 2 to t by 2, the result will be same. There will be no difference in result, but this period, for example, minus t by 2 to t by 2 is lot much easier to evaluate. So using these limits of integration and substituting from equation 3.41, we have a first k. We have first for k equals to 0. It means we are first finding a naught. So 1 over t, this is general equation we already derived. 1 over t minus t1 to t1 dt, right? So if we put the values here, so only for minus t by 2 minus t1 to plus t1 we have a value, but for other it's 0. You know that, right? Because the symmetry is in this way, right? This is your minus t1, this is the center, and then t1. So the value will only be 1 here in this range. So other part from here to here will be 0. So that's why we are evaluating between minus t1 to t1, and if you integrate you will get 2t1 over t, right? As mentioned previously, a naught is interpreted to be average value of xt. The a naught coefficient k equals to 0 is usually the average value of this waveform, right? Which in this case equal to fraction of each period during which xt equals to 1. Fraction means that you have in denominator you have a total period. So that's why you will divide by the period. So in this way you can say that it's equal to the fraction of each period during which xt is equal to 1. Here the xt is equal to 1. Otherwise, because the total period is from here to here, right? So the fraction means that it's 1 only in this region, right? So we are calculating the value in this region. For k not equal to 0, we obtain this way ak 1 over t minus t1 to t1 e minus j k omega naught t. So when we integrate, you will get 1 over j k minus 1 over j k omega naught t into e minus j k omega naught t for t1 to minus t1. So which we may rewrite after putting this value t1 and minus t1, we may rewrite is 2 over k omega naught t by just doing some mathematical manipulation, e j k omega naught t1 minus e minus j k omega t1 over 2j. So this is equivalent to the sine j omega naught t1. So we can rewrite in this way 2 sine omega k omega naught t1 over k omega naught t, right? So where omega naught t is equal to 2 pi, so when you put the value of omega naught t as a 2 pi, so the 2 will be cancelled out. So sine k omega naught t1 over k pi for k not equal to 0. This is condition because we already have an equation for k not equal to 0, which is this one. So this is valid for k not equal to 0. So k is equal to 1, k is equal to minus 1, so on. Okay, now discuss another important topic, which is convergence of a Fourier series. So convergence of a Fourier series is very much important. Otherwise, if your Fourier series is not converging, then it means that you can't calculate the Fourier series coefficients for that wave, particular wave. So we need to find that the periodic signal represented by Fourier series is equivalent to the original signal. So if you are representing, for example, the square wave with the equivalent Fourier series signal, so it must be equivalent to the original signal, square wave signal, for example. For example, specifically in case of square wave, which has discontinuity at some points, so we have to find that whether they are convergent or not. So how we can find that the Fourier series is converging or not? So the criterion to find the approximated error is to use the energy in the error over one period. So the criteria is you can find the total energy over one period. So thus the way is to choose the coefficient such that it can reduce the error energy. So we have to select the coefficients AK, A2, it means A1, A2, A3, A1, minus 1, minus 2, minus 3 in such a way that it can reduce the error energy. What is error energy we will discuss later. So thus if the number of harmonics in Fourier series n increases, it will reduce the error energy. So if n is approaches infinity, then error energy approaches to zero. When to use the Fourier series? Usually for any signal we can use it, but usually from some signal it diverges. That is, from some value of AK it usually results in infinity. So it happens that when you find the coefficients AK, usually uh, it is giving some finite value, but for some particular K, it may diverges. It means that it doesn't have some finite value. It is equivalent to infinity. So for that, when a coefficient, it means that series is not converging. Sometimes even the values obtained of AK are not infinity, but still they don't converge to original signal. So sometimes it may be a case that AK is not exactly equal to infinity, but still we say that the signal is not converging. Now let's discuss the summary and how to find the error energy as we discussed earlier. How can one guarantee that the signal represents, this is Fourier series, represent a periodic signal xt? So let us use an engineering tool named approximation error. So if you have less error or the very minimum error as compared to the original signal, it means that you have correctly represented the signal, right? Assume that a periodic signal can be expressed by a linear combination of limited complex exponential terms. For example, minus n to n, you can say that the periodic signal can be expressed in terms of Fourier series coefficient as well. So approximation error in this way is defined as original signal minus the approximated in the n is, for example, n is equal to 20, n is equal to 30, right, in this way. So you have to find the approximation error. So the energy of the error in one period, this is your signal energy, right? If you want to find the energy, you have to scale that one, right, over the period. It can be shown that to achieve the minimum error energy, one should define that AK is this one, and as n approaches to as n increases, error energy decreases. And we can say that if n approaches to infinity, this one, so we have error energy approaches to zero. So this was the concept for the convergence of a Fourier series. So if you are increasing the n, error energy is decreasing. It means that that signal Fourier series is converging. So class of convergence. There are different classes of convergence that a periodic signal satisfy to guarantee that it can be represented by a Fourier series. So there can be different classes, and if one of them are satisfied, it means that the signal is converging. For example, it must have a finite energy over a period. If you have a given period, for example t, and if you calculate the signal of that energy of that signal, which if it comes less than infinity, it means that it's converging. This condition guaranteed that the coefficients obtained are finite. Finite means converging. Furthermore, it must also ensure that energy of the error should be zero. And if you calculate the difference between the original signal and the approximated signal, it means that the Fourier series approximated signal, if you find their difference and then calculate the energy by taking square, and if it is zero, it means that signal and its Fourier series are same, are indistinguishable. It means that they have a no error. Uh, let's discuss diagonal conditions. These are the important conditions. If the Fourier series or the signals satisfy this condition, then it means that the Fourier series is valid. For example, condition over any period, the given signal must be absolutely integrable. For example, you have a x of t and you take the absolute and then take the integral of that signal. If it comes less than infinity, it means that uh, the it satisfies the diagonal condition. So by considering square integrability, this guarantees that each coefficient will be finite. The condition of square integrability is that square integral, so f of x and whole square and less than infinity. The signal which does not satisfy the condition 1 is shown in figure below. So for example, you have a x of t 1 over t, and if you take the integral of this signal like 1 over t dt, and from 0 to 1, because its period is given 0 to 1, and if you integrate you will get log of t. So when you put this limit 0 to 1, you will get infinity. It means that this signal is not in absolutely integrable, so it is not possible to find the Fourier series of that signal. So the first condition is that if it must xt must be absolutely integrable, right? So this is the signal that violates the condition 1 at some point. For example, if you can see that here it is fine, but when it comes to minus 1, it goes to infinity. And then it here is fine, but when it comes here, it goes to some large values, right? For example, this large values. So another condition is that in any finite period, there should be a finite number of maxima and minima. For example, there is a there can be a maximum one or two maximum points, but if there are a number of uncountable maximum and minimum point within a specified period, for example, when you have a period of 1, period of 2, and if the result is huge number of maximum and minimum points, then for this signal the Fourier series is not possible. For example, the signal which breaks this condition 2 is that xt sine 2 pi over t. Let's see how it breaks the condition 2. Okay, the signal that violates the condition 2 is this one. If you see that this point, they have a number of maximum and minimum. This point, they have a number of maximum and minimum. So in the Fourier series of this signal is not possible. The other condition is that in any finite period, there should be finite number of discontinuities. Finite means one or two, but if there are number of discontinuities, then for that signal, it's not possible to find the Fourier signal. So the signal which breaks the condition 3 has the period 8, but it consists of infinite number of discontinuities in each period. Let's see the signal. This signal. This has a period 8, for example, here to here, but you can find the number of discontinuities in this way. That's right, these steps are actually the discontinuities. So their discontinuities are infinite. X3 satisfies that its Fourier series equivalent signal except at the point where X3 is discontinuous. So we can't find the Xt Fourier series coefficient at that discontinuous point, so it's not possible to find the Fourier series. So at the point of discontinuity, it converges to the average value of either side of the discontinuity. So these were some conditions which must be remembered to find the Fourier series. If these conditions are not satisfied, it means that the Fourier series is not possible. Thank you for listening, and for Q&A session there will be a separate slot. Thank you very much.